So it's time to start the afternoon session. As a final talk for today, we are happy to have Xiaogan Wen from MIT that is going to speak about a 6-year journey from gravitational anomaly to unified theory of generalized symmetries.
Okay, yeah, I'd like to thank organizer for organizing this really very timely conference on this very rapidly developing field. I also like to thank organizer to give me a chance to give this online talk. I'm very sorry I couldn't be there. And so today I will mainly talk about a unified theory for this generalized symmetry, which include higher symmetry, non-invertible symmetry, and anomalous symmetry, and all that. You know, for us, at the beginning, we first have this, we try to develop a general theory for non-invertible gravitational anomaly. And then later we realized that this non-invertible gravitational anomaly turns out to be symmetries. So therefore, the theory for non-invertible gravitational anomaly became a theory for symmetries. And so then we start to using this point of view to understand the symmetry and generalized symmetry. So I will first discuss, give a very brief discussion of the non-invertible gravitational anomaly. But before that, I need to give a discussion of topological order. These two are very much related. So, you know, in condensed matter, for a long time, we think this lambda symmetry breaking theory describe this all phase of matter and their phase transition. But however, after discovering of fractional quantum Hall states for two-dimensional electron gas, we realized that there are some systems like two different quantum Hall states have exactly the same symmetry. So they are beyond the Landau symmetry description. So therefore, they must contain some new kind of order, which we call topological order. The topological order turned out to be very rich. It's even include something like non-abelian statistics. For example, in this two paper on 1991, and this concrete wave function was constructed. And so those concrete many-body electron wave function would contain excitations which have a non-abelian statistics. And so this is something really interesting to find those kind of states in experiments. So because this topological order is very rich, so it's nice to have a systematic theory to describe topological order, this new kind of order. And for that, we need a systematic characterization. So the beginning of systematic characterization was defined by putting quantum Hall state on the sphere, on the torus, on the genus Riemann surface, etc. And then measure the ground state degeneracy. The quantum Hall state have an energy gap. And the ground state, but however, ground state may have a degeneracy for different topology of a space. And this topology dependent ground state degeneracy can be used as a way to systematically characterize a topological order. Certainly, this idea is motivated by the Witten's topological quantum field theory, which is developed a year ago. So motivated by this kind of ground degeneracy, we can develop a systematic theory we call the modular bundle theory for topological order. And this idea is that you know, for every gapped Hamiltonian, we have a degenerate subspace for the ground state. And then if you modify the Hamiltonian, the degenerate subspace would change. And so at the end, we get a vector bundle over the moduli space formed by gap Hamiltonians. Okay. And this vector bundle contains a lot of information, and that can be a systematic theory for topological order. So this is a ground state-based theory for topological order. And there's another theory, it's excitation-based, like anion non-abelian statistics. And those anions described by their fusion and braiding, which gave rise to a modular tensor category theory. So that's also became a systematic theory for topological order. So let me describe this modular moduli bundle theory in a little detail. And because the moduli bundle theory basically is a vector bundle over moduli space, so we need to characterize their holonomy, which we call non-abelian Barré space. It turns out that if you go around the contractible loop in the moduli space, this holonomy is just a U1 factor, it's a diagonal U1 factor, and which encode this gravitational sum term and the chiral center charge of this topological order. However, if you go along a non-contractible loop, then we get a non-trivial non-abelian matrix. And one of a non-contractible loop can be constructed in the following way. So the vertical direction is time direction, sorry. And so we have the space is a torus. We just deform the system in time direction, then we glue two systems back via the mapping class group. And that's give rise to the non-contractible loop in moduli space. So therefore, this holonomy on non-contractible loop actually is a representation or project representation of a mapping class group. So therefore, we can use a representation mapping class group to characterize topological order. So this became very detailed and quantitative characterization of a topological order. And for the extension-based theory, this multi-tensor category theory actually have a very interesting history. And the first, the multi-tensor category theory was developed for rational conformal field theory. Then later, after Witten's work, we realized that this rational conformal field theory and the topological quantum field theory have very close relation. And the topological quantum field theory really describe anyons, have anyons in it. And so therefore, it's end up that this multi-tensor category theory developed for rational conformal field theory became a theory for anyons. And that led to this more general theory of a topological order based on the excitations. In higher dimension, we can have a point-like excitation and a string-like excitation. And so therefore, those anyons or excitations, topological excitations, form a higher category theory. More precisely, form a non-degenerate Bragg diffusion higher category. And that became a theory for topological order in higher dimensions. So that's just a quick summary of a topological order. And recently, using this modular bundle theory, basically using the SL2Z representation in 2 dimensions for 2-dimensional space, we can classify topological order up to 11 type of anyons. Okay, and this classification led to this this systematic understanding of gapped quantum phase in condensed matter. You know, in string theory, there is a holographic principle. That is, the boundary CFT is equal to bulk ADS gravity. There's something like that. However, in the topological order, we also have a holographic principle. That's basically saying that the boundary determines bulk, but the bulk may not determine boundary. Okay. And mathematically, it's really, this statement really means the following. You know, the excitation in the bulk topological order are described by the Bragg diffusion category called M. And the excitation on the gap, the boundary, is described by the fusion category F. So this boundary bulk relation basically say that the boundary fusion category determine the bulk Bragg diffusion category, and which basically is given by this center functor, which is generalized Greenfield center. Actually, this boundary bulk relation can be derived using this using operator algebra formalism. We just heard a talk about that. So basically, for the boundary excitations, and we can use a string operator to create a pair of excitation on the 2 string end. And those string operator satisfy some algebras. And this algebra actually encode Bragg diffusion category. So using the operator algebra approach, one can derive this boundary bulk relation. So in a sense, this boundary bulk relation really is a generalization of anomaly inflow. That is, when the boundary theory have a non-trivial bulk, we say this boundary have a gravitational anomaly. Okay, and And in general, those gravitational anomalies are non-invertible because the bulk topological order is not invertible topological order, is not invertible. So this really led to a general classification of a gravitational anomaly. Basically, gravitational anomaly is the same as a bulk topological order. And this picture was used to classify a topological order in 3+1 dimensional. This is really because in 3+1D, we can classify there's some particular class of a boundary of a 3+1D topological order. And from those classification of a boundary, that's led to the classification of a bulk topological order. Basically, we find that if a 3+1D topological do not have any emergent fermions, if all the particle-like excitation are bosonic, then those 3+1D topological are classified by 3+1D Dagrange-Witten theory for finite group. However, if a theory have an emergent fermion, the classification can also be done, but it's more complicated. So I will not state here. So the question here, yeah. So this basically is a brief summary of a topological order and a gravitational anomaly. So we understand the gravitational anomaly in a strange way as a bulk topological order, not as a non-invariance of a diffeomorphism. So this is quite different from the usual point of view. Okay, so now we want to use this gravitational anomaly to understand the symmetry. So so usually we have this long-standing theoretical challenge, which is how to understand the gapless state in a very systematic way. Because for gapless states, this theory of topological order really describes a gapless state very systematically and quite completely. So we feel we have understanding. But for gapless states, we have trouble. We don't have a systematic theory for all the gapless states. Okay. And how to make a progress in this direction? The one idea is that to using the emergent symmetry in gapless states. For example, for electron system in one-dimensional lattice, we have a Fermi surface, two Fermi point, basically have right mover, left mover, and then we know that the lattice symmetry, like U2, is became enlarged to the U2 symmetry for the right mover and U2 symmetry for left mover. So this will be the example for emergent symmetry. In recent years, we find that emergent symmetry can be very general, can be anomalous symmetry, can be higher form symmetry, can be higher group symmetry or non-invertible symmetry, and all these are very, very general symmetry. And so because emergent symmetry is so general, so maybe it's a pretty complete calculation of gapless states. So the one idea is that to conjecture that this maximal emergent symmetry can largely determine gapless states. So therefore, instead of studying gapless state directly, we will study maximal emergent symmetry. And a classification of a maximal emergent symmetry is almost like a classification of a gapless liquid states. So this is one big motivation to study the generalized symmetry, because we want to understand a gapless state. So but we have so many different generalized symmetry. So we want to have a unified theory for all those generalized symmetry. Certainly group and higher group is not enough. We need to find something beyond that. And so one idea is to classify this so-called anomaly-free non-invertible higher symmetry. So instead of study classify most general non-invertible symmetry, let's put in anomaly-free condition here. Okay, but what is anomaly-free means for generalized symmetry? Anomaly-free basically means that this symmetry contain a symmetric product states which have a trivial topological order. And to make this statement more mathematically, more macroscopically in field theory, we can say that a symmetry G is anomaly free if there exists a system with that symmetry. such that that system have a unique gapped ground state on closed space of any homotopy type. So basically, this particular symmetric system allow non-degenerate gapped ground state for arbitrary space topology. Okay, and such a symmetry will be anomaly free. Okay, it turns out that we can describe anomaly free symmetry using conservation law, because we have this unique ground state. On top of unique ground state, we have a lot of excitations. And those excitations form a fusion n category if the space dimension is n. Okay. And then we can use this fusion n category to describe symmetry. Okay. But however, for anomaly free symmetry, not every fusion n category is allowed. It's only a particular class of a fusion n category called the local fusion n category, which basically classify the anomaly free non-invertible higher symmetry. Okay. So this local really means that this fusion category have a fiber functor mapped to a vector space. Yes, please.
We have a question.
Yeah.
Hi, I have a very basic question. Is there a physical reason why one should only consider fusion higher categories, so semi-simple ones?
Yes. Yes and no. Maybe here when I say fusion n category, I kind of assume the number of objects and the morphism could be infinity, and that is necessary for the continuous symmetry. But that theory is not fully developed. So so here in many cases, I will assume we have a finite symmetry, and so therefore the number of topological excitation or number of symmetry charge are finite, and that became more standard fusion n category. And but when I say fusion n category, sometimes I may mean fusion n category with an infinite number of objects and a morphism.
It's a simplifying assumption.
Yeah. No,
Thank
I
you.
don't know what is the general theory for this category with infinity object, and this is a very important open question. So therefore, the unified theory I'm describing here are mainly for finite symmetry. For continuous symmetry, we need this category with infinite object to really do the job. And we don't have a mathematical theory in that direction. And to explain this fiber functor in physical sense, let's consider we have SU2 symmetry where we have a spin 1/2 excitation, which form two-dimensional representation of SU2. If you break the symmetry, then this 2D representation of spin 1/2, the split into two direct sum of two 1D representation of nothing. Okay. And this trivial 1D representation really corresponds to excitation in it's n-vec. It's just a vector space. So therefore, physically, this fiber functor really means this symmetry breaking process. So requiring to have a fiber functor really means that this anomaly-free non-invertible higher symmetry is breakable, and we can break it into a case with no symmetry. So that's a motivation why we use a local fusion n category to classify anomaly-free symmetry. And this definition of anomaly-free actually is quite reasonable in a sense. All the anomaly-free non-invertible higher category theorem, higher symmetry can be gauged. They can always be gauged. And the one way to gauge it is to think we start with a trivial product states, where there's the charge are described as a fusion n category, which describe this symmetry. Okay. And to gauging this symmetry means that after gauging, we'll get a non-trivial topological order, and which this topological order actually is called the R gauge theory. Okay. So what is this topological order? Well, the construction topological order have this. You can using this slab construction. That is fusion n category have a non-trivial center or non-trivial bulk, which is called the ZR. And then we can stack two fusion. We can have a two boundary for this center, both are equal to R and R reverse. And so this stacking of these two fusion categories via this center is written in this way. Okay. And this is basically gauging. So that is R gauge theory is this slab construction. Okay. And from this slab construction, we can also define what is anomalous symmetry. Okay. And this motivated, actually many speakers in this meeting talk about the difficulty to define what is the anomalous symmetry, in particular for non-invertible higher symmetry. And here we just propose a particular way. And we kind of assume this anomaly is invertible. So therefore, after we get this R gauge theory, we can do some invertible twist and to get the Daggra-Witten theory, the corresponding Daggra-Witten theory of this R gauge theory. And this invertible twist very naturally can be chosen to be an automorphism of the bulk of the center. Okay. So therefore, in our definition, anomalous non-invertible symmetry is given by the local fusion N category and automorphism of its center. And there's a slight subtlety, that is R symmetry in one higher dimension is no longer called R symmetry, it's called sigma R symmetry. The sigma is a delooping. Okay. So therefore, this automorphism actually is not the center for R, but the center for sigma R. Yeah. So this is a little bit subtlety because a shift of a dimension. And so from here, once we get this Daggra-Witten theory, then we can view the boundary of a Daggra-Witten theory would have anomalous higher symmetry. So this will be the the boundary of this theory will be describe anomalous non-invertible higher symmetry. And so this led to this conclusion that in this for this invertible anomaly, then the anomalous n+1d non-invertible higher symmetry are classified by this pair. And the R is the local fusion N category, and alpha is automorphism in the center of a sigma R. And we also have this this classification of anomaly-free symmetry, which is just a local fusion category. So looks like this is a pretty complete story, but actually the emerging symmetry can be even more general. That's in addition to anomaly-free symmetry and anomalous symmetry, we also have beyond anomalous symmetry. There are some symmetry which is beyond the anomaly defined here. Now, certainly we can generalize definition of anomaly, including this beyond anomalous symmetry as anomalous symmetry, but using invertible anomaly, that's not general enough. So we also have this beyond anomalous symmetry. So then what is a general theory for this beyond anomalous symmetry? Okay, so this led to this symmetry topological order correspondence. That is, it's a holographic picture of the symmetry. We already see this use of holographic picture in definition of gauging and the definition of anomaly. And but actually we can have a more general systematic theory for symmetry using this holographic picture. Actually, in last many years, there's many different versions of this holographic picture, like this isomorphic decomposition, or like this non-invertible gravity anomaly, which you just mentioned, or like a braid fusion N category, and etc. Okay. So first, I will try to describe this holographic picture using this point of view of a non-invertible gravitational anomaly. Okay. So usually a symmetry is defined by the commutative operator. We have an operator which commutes with Hamiltonian, so that means a symmetry. Okay. So now we'll take a little bit different, unusual way to look at a symmetry. That is, we only consider a symmetry in a symmetric subspace, sub-Hilbert space. That is the sub-Hilbert space which are invariant under this symmetry transformation. Okay. So physically, this really means that both our system and our probing instrument respect symmetry. So we cannot look into the symmetry. Symmetry transformation actually break the symmetry. You have to break symmetry to do transformation. If you don't break symmetry, you cannot do transformation. And we only have the access of this symmetric sub-Hilbert space. Okay. So then from this point of view, we have some trouble because the symmetry operator, all different symmetry would act trivially on the symmetric subsphere space. We cannot distinguish different symmetries. So how to identify the symmetry group, And so then the idea is that the total Hilbert space of a lattice system have a tensor product decomposition, where this Vi is a small Hilbert space on each lattice side. The total Hilbert space have a tensor product decomposition. So this is a statement of anomaly-free condition for gravitational anomaly. Means a model can be really realized on the lattice in the same dimension. Okay, but however, for the symmetric sub-Hilbert space, because we do this projection, and they no longer have this tensor product decomposition. And so this lack of a tensor product decomposition means a gravitational anomaly. Okay, means we cannot have a lattice system whose lattice Hilbert space realizes this symmetric Hilbert vector space, Hilbert space. Okay, so this really gave us a motivation to say that the symmetry is kind of same as a non-invertible gravitational anomaly. Okay, and also it's quite well known that the gravitational anomaly is same as a topological order in one higher dimension. So this I already mentioned that that's because it's a holographic principle in topological order. Okay, and actually this can be checked. When you have a topological order, we have a very large gap. Sorry. Then there's a boundary. Hilbert space which have a lower energy, and it turns out that this boundary Hilbert space don't have a lack of a tensor product decomposition as described in this paper. Okay, so this really means that the lack of a tensor product decomposition really means that the system can be viewed as a boundary for topological order in one higher dimension. Okay, so this really led to this belief that the symmetry really described by a topological order in one higher dimension. So what that means when you say symmetry are described by topological order in one higher dimension, here's a more precise statement. A system with a general symmetry will restrict to this symmetric sub-Hilbert space, and then it can be fully and exactly simulated by a boundary of a topological order. Okay, so that is a more precise statement. Okay, so because this is close relation, this topological order is called the symmetry TO or symmetry TFT. Okay, and I want to say that originally in this 2019 paper and 2020 paper, we call symmetry TO or symmetry TFT by a name categorical symmetry. But nowadays, the categorical symmetry was used mainly to refer to non-invertible symmetry rather than topological order in one higher dimension. So we stopped using categorical symmetry to refer topological order in one higher dimension. So we use symmetry TO or symmetry TFT. And these two names are basically the same, but however with a slightly different emphasis. Here, symmetry TO really emphasizes that this topological order have a lattice completion, have UV completion by a lattice, and also this lattice UV completion have no symmetry. There's no additional symmetry at the lattice UV completion level, and also because it's a lattice, basically it's a lattice model. So therefore, the symmetry TO may or may not have a field theory representation, because the correlation can be zero. So it's hard to define any field. Okay, so this really what I mean by this symmetry TO correspondence. Okay, to really describe this symmetry TO correspondence more precisely, we need to introduce a notion of this hollow equivalent symmetry. Okay, So the two symmetry are hollow equivalent. If there's a symmetric system have a one-to-one correspondence, we know that each symmetry does not mean one system. Each symmetry have many systems. However, when we have a two symmetry, that means we have a two class of system. And these two class system have a one-to-one correspondence, such that for the corresponding system, when we restrict to this symmetric subspace, the corresponding system are identical. So that is the definition of a hollow equivalence. After restricting to symmetric subspace, the two systems became identical. And because this restriction, there's some unexpected result. Actually, we already heard in the last talk. That is from the Z4 symmetry and the Z2 cross Z2 symmetry with a mixed anomaly in 1+1D are hollow equivalent. Okay. And also, the two anomaly-free non-invertible higher symmetry described by two different fusion categories are hollow equivalent if they have the same center. So basically, hollow equivalent means when they have the same symmetry TO, they will be equivalent. So that's why the motivation to call this a holographic equivalence, a hollow equivalent. Okay. After introducing this hollow equivalence of the symmetry, then we can say that the generalized n+1D symmetry up to this hollow equivalence are classified by this braid diffusion N category with a trivial center and in trivial width class. And for finite symmetry, this braid diffusion N category basically means a topological order in one higher dimension or symmetry TO. Okay, so this is a more precise classifying statement about generalized symmetry. So certainly, I want to emphasize again that not every topological order in one higher dimension describes general symmetry. Only topological order with a gapable boundary, or in other words, in a trivial width class, correspond to generalized symmetry. Okay, so here here we have a classification for 2+1D topological order, and only a small subset of them belong to trivial width class. And those are correspond to generalized symmetry up to hollow equivalence. For example, for topological order of rank 4, we have a 3 class of generalized symmetry. And one of the 3 class is a Z2 symmetry. Another one is an anomalous symmetry, and the third one is this Fibonacci symmetry. Okay. And
sorry, Xiaogang.
Yeah.
Just one. Can you go back one slide?
Yeah.
The rank. How do you define it? Is it the number of simple...
rank is the number of anions in topological in the topological order in one higher dimension. Another way to say that is the number of symmetry charge in the symmetry defect and their combination. Yeah, so this holographic picture or symmetry TO picture really view symmetry defect, symmetry charge at the equal footing, and also view their boundary, their bound state together.
And how would you generalize that to higher dimensional cases? Because in the 3D 2D case, there is only the anions, but in higher dimensions there are.
Yeah, this is a very, very good question. How to define a number of anion in higher dimension? In particular, we have an infinite number of condensation defects that became difficult to do, and I tend to use the so-called elementary excitation, so that the excitation which is not coming from condensation, which don't have a boundary. So like in 3 dimensions we may have a string excitation, but this string excitation cannot have a boundary. Those string excitation which cannot have a boundary, it can be called elementary, which basically gauge flux. That's what we usually say. And maybe counting number of so-called elementary excitation is a way to define rank of higher category theory. And this number of elementary excitation is maybe finite, at least for finite theory. But indeed, this is a very, very good question. So in 2+1 dimension, we have a simple picture. Yeah, thank you.
Thank you.
Okay, so so let's discuss this Fibonacci symmetry in more detail. And actually, Fibonacci symmetry is described by this the symmetry TO, which is a double Fibonacci topological order. So it means this topological order is generated by a Fibonacci anion we call the phi, and another independent Fibonacci anion we call phi bar. And these two phi and phi bar, their spin have a different sign. Their statistics is a complex conjugate. Okay, and and then we can using some lattice model, which is called the Levin-1 model, to realize this double Fibonacci topological order in this slab of a 2+1 dimensional lattice. Okay, then on this two-dimensional lattice, we have a top boundary. It's a boundary with a very large energy gap, which is generated from the condensation of a phi bar. If you condense phi bar, you would break this topological order completely, and so therefore this condensing phi bar would generate a gapped boundary. And a lower boundary, this red boundary can be any low energy theory, any low energy boundary. This kind of give rise to low energy effective theory. Okay, and this slab actually, although it's a 2D system, but when the slab is very narrow, can be viewed as a very long 1D system. So this is the lattice realization of this Fibonacci symmetry. And in this lattice realization, what is symmetry transformation? The symmetry transformation basically is a string operator in a bulk, which create a string operator which create a pair of phi anion or phi bar anion. Those string operators which generate symmetry. The symmetry charge basically is a bound state. Phi bar is a bound state of this bound state is a symmetry charge. And any local operator on the lower boundary commute with this string operator in the bulk by definition. So they are symmetric. They are local symmetric operators. So basically, this is a very concrete realization of this Fibonacci symmetry. Again, using this holographic picture. It turns out that this picture can realize any non-invertible higher symmetry. They're just using this idea. Okay, so far I've described a general theory for non-invertible higher symmetry, but the general theory so far is not very detailed. There's only distinguished symmetry up to hollow equivalence. So we can describe a more detailed theory of this symmetry. And this more detailed theory is developed by trying to define the morphism between topological orders. Okay, so this we know that a morphism is a very important concept. That like morphism between group theory, between two groups, just preserve a multiplication structure, between algebra, preserve algebra structure. So therefore, it's actually maybe one of the most important concepts in mathematics, the structure preserving map. And to define the homomorphism between quantum field theory, we first need to know what kind of property you want to preserve, what kind of structure you want to preserve. Okay, so that's led to this notion of a hollow equivalence, but between quantum field theory, or the notion of so-called local low energy property. So actually, it is a local low energy property that we want to preserve. Basically, the local low energy property means that we have a set of local operator for general system, or we have a set of a local symmetric operator for symmetric system. And the correlation function of those local operator or local symmetric operator are so-called the local low energy properties. And those are properties we want to preserve. If two quantum field theory, their local operator have a one-to-one correspondence, and their local operator have a same correlation function, then we say these two quantum field theory are local low energy equivalent, or maybe a hollow equivalent. So basically, we mean that if we have a quantum field theory, we start with a gapped quantum field theory and assume this gap is very big. Then this stacking of a gapped quantum field theory do not modify this local low energy property. So that's basically is a hollow equivalence. So stacking with a gap theory, or stacking with TQFT is a hollow equivalence relation. Okay. So so using this idea, we can define the hollow equivalence between two anomalous quantum field theory. So far this discussion is for anomaly-free quantum field theory. We can define the hollow equivalence between two anomalous quantum field theory. Anomalous quantum field theory means that we have quantum field theory with non-trivial bulk. So their boundary of a bulk topological order have non-trivial bulk. Then the hollow equivalence for this anomalous theory means that we stack with a gapped domain wall between two different bulk. Okay, and so this R tilde is gapped domain wall, and then this composition of R tilde M and QFT is same as QFT prime. So therefore, this square point is an isomorphism, and so this isomorphism is an equivalence between two quantum field theory, and this quantum field theory only differ by stacking with a domain wall, a gapped domain wall. So this kind of equivalence we call this isomorphic holographic decomposition. So if the quantum field theory can be decomposed in this way, then we say that the two resulting quantum field theory are hollow, have this homomorphism. So therefore, this domain wall and this isomorphism define a homomorphism, which between these two anomalous quantum field theory. And this concept turns out to be very important and also very useful. For example, we can use this concept to derive the notion that the bulk of a quantum field theory, this concept of taking a bulk is same as taking a center, a generalized dream field center. And there's many other results in recent years kind of derived from this homomorphism. And here we are going to use this homomorphism or this isomorphic holographic decomposition to formulate a general theory of the symmetry. Okay, so basically it's very simple. If you have a quantum field theory, and we find this quantum field can be decomposed at this stacking, as this R tilde stack with M with another quantum field theory. And then we say this decomposition expose a symmetry in this quantum field theory. And the exposed symmetry have a symmetry TO. This bulk M happen to be the symmetry TO we mentioned above. But also in this picture, we can see that in addition to the bulk, we also have the other boundary. So therefore, this pair form a more complete description of a symmetry. So this pair is called a quiche. So that's pronounced a quiche. And so in the Friedman-Telemans paper. And here we want to say that because this M is a bulk of this R tilde boundary. So therefore, the M is a dependent R. It's a center of R. So in some sense, we can just say this general symmetry is classified by this fusion N category. Okay, so here we don't have a local condition. Just a fusion N category would describe this generalized symmetry. So this led to this more general description and also more detailed description of symmetry. But however, there's a little problem with this description. It seems too general. And so to understand this issue, let's consider a system with no symmetry. So suppose we have a system quantum field with no symmetry at all. So that means that their symmetry TO is a trivial. So there's a trivial bulk. The bulk just a trivial product states, no symmetry. But however, in a higher dimension, we can have a boundary, a non-trivial boundary described by some topological order, like quantum Hall states. We have infinite number of them in higher dimension, and that's this boundary have a trivial center because symmetry TO is a trivial, have a trivial center. So do we view this R tilde TO as a symmetry? You know, if you're using fusion n category to classify symmetry, this will be a symmetry. But we start with a system with no symmetry. Then we say a system with no symmetry have infinite many symmetry described by braid fusion category with a trivial center. So this is a little bit kind of strange. So certainly mathematically, it's okay to define fusion n category as a symmetry, but physically, we want to remove. We do not want to regard this kind of a fusion n category as a symmetry. Basically, we do not want to regard the fusion n category with a trivial center as a symmetry. We want to remove that. Actually, I don't know how to remove that. And here we just have a very crude proposal, which may or may not work really. But the proposal is that we can define some kind of order, a strict order for the fusion n category. And we say if a two fusion category R is less than R prime, if R prime can be viewed as stacking of R with another non-trivial fusion n category that have a trivial center. Okay.
Question?
Yes.
Would it be sensible to demand some sort of non-degeneracy condition by demanding that the symmetry must act at least on some operators in your theory? Because that would get rid of this case, right?
Yeah, maybe. We cannot say the fusion n category is non-degenerate, because the fusion n category is non-degenerate. That's basically is a fusion n category with a trivial center. So you want to get rid of fusion n category. We want to get rid of fusion n category. Oh, it's yeah. So I don't know how to do this, but this is just a very cool thing. And my purpose here is to expose a problem. And I think this may be an open question, and hopes people in mathematics can really formulate some more precise way to handle this. Yeah, but there's an issue here. I just want to say. Okay, so then using this order, strict order, then we can define so-called minimal fusion n category, which get rid of those this R tilt TO. And certainly minimal one is not unique. There's many minimal one, and so those minimal fusion n category describe symmetry. So that's a kind of a hand-waving fix of this problem. And this fix actually is necessary in a sense, because once we have this fix, we can have a very simple statement about the symmetry protect gaplessness. Again, this is
we have one more question. Sorry.
Yeah, please. Yeah, please.
Hi, could you say again what it means to be minimal for a fusion category?
Minimal means that we first define this inequality, this ordering of fusion category. Then using this ordering, we define the minimal one. So the one which which don't have anything smaller than that. The fusion category which don't have anything smaller than it.
And what's the definition of the order?
Order is this. R prime is bigger than R if R prime equal to R tensor product. This is the Deligne product with a fusion n category with a trivial center.
Thank you.
Yeah. So this is a way to define order. This may work, but I'm not so sure. But this is a proposal. Yeah. And so how to understand the symmetry product gapless? The symmetry product gapless in general setting, there's two types. There's a, when I say symmetry product gaplessness, really means the state do not break symmetry. But what symmetry we do not break? So in the first type, we say that our state do not break symmetry TO. When the system have a symmetry, it have many different states. Some state actually breaks symmetry TO. And so we want to consider state which do not break symmetry TO. And that means that the following. Because our system or the ground state is the boundary of a symmetry TO. So not breaking symmetry TO means that this boundary do not contain any condensation of a bulk excitation. So that's called one condensed boundary. Okay. So state that do not break symmetry TO is called one condensed boundary. And then here the claim is very simple. Any one condensed boundary are gapless. So in other words, the state with the unbroken non-trivial symmetry TO is always gapless. So that's the one general statement of a symmetry protect gaplessness. And the one condensed boundary is gapless is called a topological weak rotation in the Liang Kong and Zheng Hao's paper, and they have quite a few papers studied this phenomenon. Okay, and this we can also prove this in some physical sense. This one condensed boundary is gapless using some kind of holomorphic using the modular bootstrap, yeah, in this paper. However, there's also a type 2 symmetry protect gaplessness. And in this case, we do not demand symmetry TO is unbroken. We demand a symmetry is unbroken. So again, we have this system have a symmetry, have many ground states, but the ground state may spontaneously break the symmetry. And here the symmetry are described by this R, described this top boundary. The symmetry described by R. And then we want this lower boundary. This lower boundary do not break symmetry. But what do you mean by the lower boundary do not break symmetry? And that means it's really the definition is really means that following. That's there is no excitation which condense on both top boundary and the lower boundary. And this is definition of a no symmetry breaking. Yeah, no spontaneous symmetry breaking in the lower boundary. Okay. In case, for example, we can choose a lower boundary to be reverse of a top boundary. And in this case, in this extreme case, every excitation which condenses in the top boundary also condenses in the lower boundary. And this state happens to describe a symmetry break, spontaneous symmetry breaking state, which completely break the symmetry. And so this is this is extreme case. And the no symmetry breaking case that is a condensation on the top boundary and the condensation on the lower boundary is totally non-overlapping. That is a symmetry non-breaking. And then the claim here is that the state with unbroken symmetry is gapped if and only if this R is anomaly free. So only anomaly free symmetry support a symmetric gap space. Every anomalous, every symmetry which is not anomaly free cannot have a symmetric gapless state or gapped states. Okay, but for this statement to be valid, it's important to require this R, this fusion n characteristic to be minimal. If R is not minimal, this statement is not correct. Yeah, please go ahead.
Sorry to interrupt. Since you cannot see us, but to every speaker received a 5 minutes warning before 5 minutes to the end of their talk, so that they can organize.
Okay.
This is your 5 minute warning. Apologies.
Yeah.
I had to interrupt you.
Yeah,
yes.
Thank you. Yeah. Okay. So yeah, so maybe we already discussed anomaly free symmetry. And this, so in this holographic picture, we can have a more detailed description. So let's just skip this. And another important topic is this is a duality. You know, the gauging duality. You know, there's all kind of a duality, which is a very important constructing the non-invertible symmetry. Again, using this holographic picture or this isomorphic holographic decomposition, we can have very simple and systematic way to understand the duality mapping between two quantum field theory. Basically, let's assume we have a quantum field theory with this kind of holographic decomposition. Yeah. So, yeah, this quantum field theory with this kind of isomorphic decomposition. Okay. Then we can modify the top boundary. Top boundary is a gap. We just modify the top boundary, but keep M and the lower boundary unchanged. Then when you modify top boundary, then this stacking would give rise to a different quantum field theory. And these two quantum field theory actually is hollow equivalent because they only differ by some different top boundary. And these two different quantum field theory actually is called a dual equivalent, a hollow equivalent. So those are really duality we talk about in general. So this kind of definition, by modifying the top boundary, we can obtain this Kramer-Wagner duality and the gauging duality, and many other duality. Yeah. But here I want to mention that I think this duality do not include this what is the Jordan-Wigner transformation duality, because that's a mapping between boson system to fermion system, which need to generalize this notion a little bit. But that can also be described using this notion. And so basically the duality among bosonic models can be described in this way very systematically. Okay. And so actually we're using this holographic decomposition. We can also have a very general theory for gapped state and gapless states. It's actually become very simple. Suppose we have some general symmetry, generalized symmetry described by this R tilde. Then it has symmetry described by M. Then the gapped boundary of M will be the gapped face with this symmetry, with this R tilde symmetry. The gapless boundary for M will be this gapless face of the symmetry. And this sounds abstract and seems doesn't have any content. Actually, it has some content. And it turns out that, for example, we can using this picture to classify SPD phase. And to classify SPD phase, we have to do something little extra. That is, we have insert invertible domain wall in the bulk topological order. Okay. Once inserted inverted domain in bulk topological order, that kind of modification would give you rise to the SPD states, different SPD states. So this inverted domain wall in bulk topological order also led to the classification of SPD states. Okay. And so maybe using my last slide, I just want to demonstrate that. For example, this condensation picture is a pretty concrete. For example, if a symmetry TO for the Z2 cross Z2 symmetry, the symmetry TO just a Z2 cross Z2 gauge theory. Okay, and then there's 6 Lagrangian condensed algebra of this Z2 cross Z2 gauge theory, which classify the gapped boundary of this symmetry TO. And by listing these 6 condensed algebra, we can see that it have all kind of different symmetry breaking pattern. That's how the Z2 cross Z2 symmetry is broken. But also it have a particular case, which is symmetry is not broken, and this case is SPD states. So this is just an example that this using condensation and using gapped boundary, we can really classify the SPD states and the symmetric states and topological states with a particular symmetry. Yeah, the notion of SPD is introduced in these two papers. It's actually defined as a non-trivial phase protected by symmetry. If you break symmetry, it becomes trivial phase, something like that. Yeah. Okay, I will stop here. Thank you very much.
Thank you very much for the nice talk. Are there further questions for Xiaogang?
So I have a question about the classification of topological order up to rank 11. So
Yeah.
Are there any distinct topological order with the same modular data in that list?
Yeah, that's a good question. Maybe let me, strictly speaking, this classification is only for the classified modular data. And we don't think there is a modular isotope at this low level. Okay, but we are not so sure. So actually, I want to say the following: at the rank 9, 10, 11, we have some modular data with unknown modular tensor category realization. Actually, but they have a. But there is a conjecture they probably can be realized by so-called near group modular tensor, a center for near group. Yeah, but the near group, center for near group, and all those kind of things is pretty new. It's not totally understand. So there's certain modular data is not completely known, and for those modular data, there may be modular isotope, but we don't know. Yeah. But for other modular data, they are pretty well-known modular data, so there's no modular isotope. Yeah.
I see. Thank you.
Any further question? I think we are all quite exhausted by the 3 days of conference, which have been very hectic so far. So I think we should thank Xiaogang for the nice presentation once again.
Yeah, thank you very much. Yeah, really, thank you for having me.
Thank you very much.
Yeah.
And yes, we see each other tomorrow. Thank you, Xiaogang. Thank you, Xiaogang. I don't know if you can see me. He doesn't see.